What I'm going to talk about today is, well, a project that I've been working on for several years and never published anything on. There was a workshop back in Cambridge several years ago where I talked about a very early version of this, and it is now greatly improved, as I hope you'll see. So is the question about whether we should talk about retrocausality in quantum mechanics is the main issue at stake here. Okay, so the first sort of half of the talk or so will be sort of the philosophical part. I want to qualify it by saying I'm not a philosopher, and I'm definitely not a philosopher of causation. So some of the things I say will be very crude compared to what we heard from Holly just now. But I want to outline the motivations for thinking about retrocausality and talk about a way in which we can make sense of causality in a world which has potentially retrocausality. And then in the second half of the talk, I'm going to get into the technical details a bit, and I'm going to apply it specifically to the context of Bell inequality type of experiments, because that's the main context where this question has arisen. So I want to treat that case in general, and I'll say sort of some very short remarks about the case of general causal structures. Okay, so let's think about an experiment to test Bell's theorem. And here at the top, I've drawn the usual kind of structure of this. We have Alice and Bob here, who have their choices of measurement setting X and Y, and then they observe a measurement outcome A and B. And under the usual assumptions, that includes a lot, because I know there are very big debates about how to understand Bell's theorem in the literature, but so under the usual assumptions means all of that stuff, right? But Bell's theorem basically tells us that the predictions that quantum mechanics makes for these kinds of experiments when we prepare entangled states cannot be reproduced by a causal model which has the structure given in the diagram. So there's some common cause in the joint past of the two wings of the experiment that is responsible for the correlations between those two wings. I'm going to use a color coding in this talk. It's helpful for me. I don't know if it'll be helpful for everybody else, but there's going to be three types of variables we're going to consider. If something's in red, it means it's something that's under the direct control of an experimenter. So this will be something like the setting on a measurement device. The black variables are things that are only observed. They may be influenced by the things that they directly control, of course, but they're observed quantities like the measurement outcomes themselves. And then blue means some kind of hidden variable. I generally call these latent variables in the terminology of causal modeling, but there's something that's neither directly controlled nor directly observed. Okay, so we can't have this kind of causal model according to Bell's theorem. And one way of fixing this was proposed by Costa de Burgard. This is the idea of the causal zigzag. So all we do is we take this arrow here and we turn it around the other way. Okay, so the idea is that the causal influence propagates along a zigzag path from Alice's wing of the experiment to Bob's wing of the experiment. So this was actually proposed by Beauregard in response to the EPR argument, Einstein-Podolsky-Rosen, before Bell's theorem. He proposed it in the 1940s. His PhD supervisor, Louis de Broglie, was not keen on him publishing it, so the proposal wasn't published until 1953. Hugh Price has talked about this history quite a lot, and you can find out more information about it in this paper that he wrote with Ken Wharton. Okay, so that's the idea, that we just turn this arrow around and we have a zigzag. And so why might we want to contemplate that? Well, it offers the possibility that all of the causal influences operate along time-like paths in space-time. Okay, so some of those paths operate backwards in time, but they're all operating within the light cones, as it were. So a theory that operates in this way, the thought is, might be easier to reconcile with Lorentz invariance than a theory that has explicit non-local superluminal influences. Okay, so that's one of the positives of the idea. However, I don't think that we can really take the zigzag literally. Okay, so in physics, at least, normally we think of things like, you know, causality and the arrow of time as some kind of an emergent macroscopic notion. Our fundamental laws are time symmetric. So if you have some kind of an isolated quantum system, it doesn't really have an arrow of time. It doesn't really have something like that. So if you think that the causal mediaries in this diagram are supposed to be the electrons or the photons that are being dealt with in your Bell experiment, the idea that the photon that's going from here to here actually has an arrow of time that could sort of turn around one way or the other is a little bit suspect. So instead of a zigzag, what I propose is more of a block universe type of model. Okay, so the idea here is that, you know, normally in physics we think about our physical theories in terms of some state which you may be able to attach to a space-like hypersurface, which then you can evolve forwards or backwards in time all at once. But the idea here is, let's think about the laws of physics as more like something like a jigsaw puzzle, right? So what goes on in one particular region is constrained in a symmetric way by what's going on in the neighboring regions. Okay, and we want to try and build up the laws like that. In particular, if the past can constrain something that happens in the future, then in this kind of framework, you could also symmetrically have what goes on in the future constrain what happens in the past in a symmetric way. Now, if you adopt this kind of framework, then, you know, in general, it would be possible to, you know, influence the past by changing what goes on now. Okay. In fact, we can't do that, right? So in fact, we can't send signals backwards in time, for instance. But the idea here is that the ability to influence the future but not the past would be explained in some kind of an emergent way, in the same sort of way as the arrow of time. You know, we currently need a thermodynamic account of the arrow of time. So whatever notion of thermodynamics is appropriate to formulate in this framework, and it is indeed not obvious, because normally when we're talking about thermodynamics, we account for the arrow of time in terms of special initial conditions, right? So here there's no privileged role for initial conditions, so it's not entirely clear what to do, but we need some notion like that. And the idea is that the ability to affect the future but not the past would be emergent from that in the same way as the arrow of time. That is an account that doesn't exist yet, but we're going to think about this sort of jigsaw puzzle block universe type of view. Okay, so let's look a little bit at the assumptions behind Bell's theorem. So there's the measurement independence assumption, right? So this is the the assumption that normally says that we don't have retrocausal influences. So it says that these hidden variables, or this latent variable, is uncorrelated with the measurement settings X and Y. Okay, so that's one of the assumptions. And then we have the actual locality assumption, which sort of screens off the two wings of the experiment given lambda. Okay, so what we're talking about here is that, in this kind of framework, in this kind of block universe framework, the measurement independence assumption is perhaps suspect. And this might allow us to get some kind of notion of locality still to happen in this framework. Of course, assumptions equivalent to measurement independence appear in almost all no-go theorems for realist models that underlie quantum mechanics. So, one of the reasons for considering this is that maybe we can get all sorts of properties of our model that we would really like, not just locality, but also perhaps evade assumptions about evade theorems about contextuality or reality of the quantum state, etc., by dropping this assumption. Okay, so I'm not here advocating that this is definitely the way to go, but I think as a possibility, it deserves to be investigated thoroughly. Okay, so I also want to try and persuade you that I'm not completely crazy. This slide doesn't manage to do that because it just, if you think this idea is crazy, then it just shows you that there's a number of other people who are crazy as well. But the point is that there is sort of an increasing amount of work where people are proposing specific concrete models that violate the measurement independence assumption in some way and are able to reproduce various quantum phenomena. To my knowledge, there is not what I would call a complete account of the whole of quantum mechanics along these lines, at least not a compelling one, but there are various sort of toy models or models for specific scenarios. And I'm also not claiming that all of these models work exactly as the authors describe. There's a lot of controversy about this kind of area, but just to show that there is sort of increasing interest in it. Okay, so here's some questions that we should ask though. So if we're going to contemplate this kind of block universe model that violates measurement independence, then first of all, how should we think about causality in this kind of theory? Do the conventional notions work? And then, most of the work has been, as I've said, about building concrete models, but we need something more than that. We need a general framework which tells us what the structure of these models should be like. This is because, we want to think about things like, well, what do we even mean by locality in such a framework, right? It's all very well to propose a concrete model, but when we drop measurement independence, does that mean that we should think about modifying the other assumptions we use as well? So I'm going to argue that actually we should do that. And if you're trying to prove whether or not a no-go theorem holds, or you're trying to prove that a no-go theorem still does hold in this framework, for instance, then you need a framework at that level of generality. So that's what we're going to try and ultimately provide. Okay, so let's think a little bit about causality, measurement independence, and causality. So if we think about, probabilistic Reichenbach's principal notion of principle of common cause, Reichenbach would say that if there are correlations between lambda and x and y, then there are three possible kinds of explanation. So one is that lambda, the latent variable, influences these measurement choices. It causes these measurement choices. And this would at least rule out complete free choice, right? So what is apparently a free choice of the experimenter is actually predetermined and caused by the pre-existing hidden variables. The other way around, we could think of x and y as a cause of lambda. That's the retrocausality option. But there's also the option that they have a common cause. So perhaps somewhere in the past of the universe, there's something which correlates the hidden variables with our measurement choices. Okay, so this would be called superdeterminism. It also rules out free choice to some degree because that common cause in the past is now partly determining the measurement choices. So we know a lot more about causal modeling now than we have previously. It is possible, in Pearl type causality to distinguish these different kinds of causal arrangements, right? So, but in order to do that, in general, you need to do more than just observe what happens. You need to be able to make interventions. And, the point is that lambda variables are variables that we, by nature, cannot make interventions on, at least right now with current technology. So maybe at some point in the future, if we know more about a theory that underlies quantum mechanics, we could actually distinguish these. But to our present state of what we can actually do in the laboratory, we can't.